Alrighty, my friends, and so begins the adventure into Sequence Land and series. We'll get there too. So our objective today is to understand and use and understand the language of sequences and how to find some terms of a sequence. So it's kind of an intro piece here. Let's figure out some vocabulary. I have a block there to block what the words are. So the words underneath there are that a sequence of real numbers, AK, these are curly braces, I can't make those, so I just go with it, is a function from positive integers, which I could write as z plus, but that'll confuse you, so I won't, to real numbers, the real numbers. So for each positive k, AK is the kth term of the equation. That sounds confusing, right? So a sequence essentially is a list of numbers. And so we have some sort of list of numbers. Let's suppose we have k squared or n squared. You can also use n, it doesn't really matter. And if we want to start listing those, so maybe A1 is 1, and A2 is 4, and A3 is 9, etc. So these are your AKs. We're going from the positive integers to real numbers, because these numbers, although they're 1, 4, and 9, which are integers, they don't have to be integers. So that's generally what a sequence is, and we'll see some of those. The recursive idea basically says that the next term depends on the previous term. So famous example of a recursive sequence would be 1, 1, 2, 3, 5, 8. If you don't know this is the Fibonacci sequence. You should be able to figure out the pattern and tell me what the next term is. So what do you think the next term is? Let's see if you can figure it out. I will never know. But the next term is 13, because 5 plus 8 is 13, and we can keep going from there. All right, now we have, generally we're going to talk about two different types of sequences here. We care most about these geometric sequences. So an example of a geometric sequence might be 100, and then 10, and then 1, and then 1/10, etc. An example of an arithmetic sequence might be 5, and then 20, and then 35, and then etc. So basically, the geometric sequence means we multiply by something each time. In the case I gave you, we multiplied by 1/10 each time. Yes, it's the same thing, dividing by 10, same thing as multiplying by 1/10, so I can always think of it as multiplication. Then the arithmetic sequence is we're adding something. Now that doesn't have to be a positive, I could add a negative number also, but you add the same thing each time. In terms of function land, geometric sequences link up with exponential functions, and arithmetic sequences link up with linear functions. Monotonic sequences. So the term monotonic is new for us, but monotonic refers to, well, mono is like one, so like one thing is going on here. So if we have a sequence that's like monotonically increasing, that means that every term is greater than or equal to the previous term. This one would be monotonically decreasing. This would be monotonically increasing. All right, for each sequence, state if we're arithmetic, geometric, or neither. List the first few terms, determine the pattern. So let's see. The first term is 2. The next term is take that 2 and multiply by -6, so -12. The next term multiply by -6, so 72, etc. This is geometric, and the pattern is times -6 each time. If we wanted to get super spicy, we could write it as AK or AN. They used N here, so I'll use N. AN is equal to, let's see, we started with 2, and then we were multiplying by negative 6. If I consider this a1 and this a2, then I need to be negative 6 to the n minus 1. Because, yeah, I'll write it down. I had a little conversation with myself. This first one is just 2. The second one is 2 times negative 6. The third one is 2 times negative 6 squared. So you notice that these numbers are 1 less than those ones. That would be what's going on there. Number 2, we have 40 we start with, and then our next term would be 46, and then 52, etc. This would be arithmetic. And we're adding 6 each time. If we wanted to write it in general, an would be 40 plus, let's see, that's 40 plus 6. That's 40 plus 6 times 2. So 40 plus 6, and that's a1, so n minus 1. I think you could figure that one out. Number 4, first term is 1, second term is 1 times 1. No, sorry, 2 times 1. My brain fell out there. 2 times 1. Third term would be 3 times 2. Fourth term would be 4 times 3, etc. Because this is a1, a2, a3, a4. So this one was 2 times 1. This one was 3 times 2, etc. That one's going to be harder to come up with an expression for the an term. That's not recursive. It is neither arithmetic nor geometric because we're not adding the same thing each time, nor are we multiplying by the same thing each time. So this one is neither. All right, let's fill in some math. A sequence AK is increasing if it passes any of the following tests. All right, now the difference test has to do with subtraction. Now, if a sequence is increasing, if I take some term, so let me write down this to get us started. A1, A2, A3. We keep going, and then we have AK minus 1, AK, AK plus 1. This could be n's also, etc. We don't know how long this thing goes. But if we have a difference means subtraction. So let's take AK plus 1 and subtract AK. If we are increasing, that number has to be greater than, perhaps equal to 0. And I'm going to use fancy terminology. For all k greater than or equal to 1. For all k greater than or equal to 1. So that means if I subtract 2 consecutive terms, do the term minus the previous term, I better get a positive number. All right, ratio test has to do with division. So if I take the AK plus 1 and I divide by AK, well, if AK plus 1 is greater than or equal to AK, because that's what we're saying with increasing, then that fraction must be greater than or equal to 1 for all k greater than or equal to 1. And then the derivative test, blank given that ax is a function that's differentiable on 1 infinity, whose value at any positive integer k is a of k equals ak. Well, let's think. What does the derivative have to be? Assuming that we have a derivative, what does the derivative have to be if we are increasing? Well, we know that already. We knew that pretty early on in this course. A prime has to be greater than or equal to 0, has to be positive, for all x greater than 1. Now keep in mind, we're thinking of this as a function a of x, not just a sequence. So the function covers, the x covers more than just integers, which is what k covers. Oh, more words. Okay, so part of the struggle of this section is there's so much vocab that we need to talk about. So you may be able to figure out what these mean, though. Bounded sequences, if we have bounded above, bounded below, completely bounded, or unbounded. So a sequence that's bounded above would be, I'm trying to come up with one that you guys would know. Okay, I came up with one. So a sequence that would be bounded above would be 1 plus 1 over k to the k. So if you thought of that as a function, 1 plus 1 over x to the x, if you put that into Desmos, you would get a curve that looks like this. If we're talking about the sequence, it wouldn't be a curve, it would be distinct points. So it would do kind of this sort of thing. The number that it would be approaching up here, it looks like 2.718, etc. That's e. So that's a curve that is bounded above. This is actually, this part is the bounded above part. Ignore this part because that's also bounded. But the bounded above means I approach something, but I can't go above it. The bounded below, I already gave you an example of that. That 100, and then 10, and then 1, and then 1/10, or something that I gave you like that. That one's bounded below, because that's never going to go below, it's never going to hit 0. So it's bounded below at 0. If we are bounded, that's, this one that I gave you was actually bounded, because we started somewhere, and we go from up from there. And then unbounded means we have no bound. So if we did maybe k sine k, that bounces and bounces and bounces and keeps getting bigger and bigger and bigger and bigger and bigger. So bounded above means we have some sort of upper limit, some sort of number we can't go above. Bounded below means we have some sort of lower limit, some sort of limit we can't go below. Bounded means we're stuck between two values. Logistic function is an example of that. Unbounded would be we just kind of keep growing, or we bounce around, we do whatever we want. All right, so determine whether the following sequences are bounded and or monotonic. So sine k over k. If we were to look at the values of sine k over k, if you want to, maybe one way to approach this is to go to Desmos and put these in. If you have sine, think of it as sine x over x. You're going to have numbers, and they're going to do this sort of thing. So that's not monotonic, but we are bounded, because we're stuck between values, but we're not kind of always increasing or always decreasing. For this one, again, if you wanted to, like a way you could think about this, there are many ways to think about this, but you put x cubed over e to the x into your grapher, and it's going to give you a graph that looks like this. So that is bounded, but we're not monotonic. That one actually we can call, though, eventually monotonic. And we can create an argument for kind of how that works. This one's going to keep growing, because if you think about x squared minus x, that's going to keep growing. So that's not bounded, nor is it monotonic, because if you have x squared minus x, it will decrease a little bit and then it will go up. So that one's neither. And then this one, 10 to the x, so graph that, 10 to the x over x factorial. And I hope you have Desmos open. Now you have to be careful, because here's the fun part. If you look at this graph, it looks like this. But if you zoom out, it goes like this, and it tanks, because the n factorial eventually takes over. So that one we can consider bounded, because it does have a maximum. If you go to your grapher and you just start increasing your y values, you will be able to figure out what the max is. It's super big, I mean not super big, but it's pretty big. Goes up to about 27, almost 2,800. So we are bounded, but we increase and then decrease, so we are not monotonic.